that clear?
Yeah, so we have to do it with a textbook, question paper. That's what we have to use, right?
It's not intelligent, for sure.
Okay. Oh, it's not intelligent yet.
Yeah, you don't have any
I'm not
intelligence.
intelligent for sure. So it's okay.
You can consult any kind of the cellulose-based medium. You know what is cellulose? Paper, okay. On the paperwork, I will ask you to sign a pledge. Okay, a pledge that I did not consult any kind of blah, 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 blah. Okay, everybody knows? Okay. I give you, the new company people, 20 seconds to read the announcement on the whiteboard.
Is the exam timed?
It's time to give you 3 hours. Okay?
And the window is?
Window is 1 week. Clear? Okay. So if I identify any issue, any person that they disobey this regulation, your final examination will be closed book in class.
For that particular person, right?
Huh?
For that particular person, right? Not
No, everybody. And I will announce who made that.
Why should I pay for someone's?
Even online student. Even online student make this kind of the disobey law, you should stay here. Anyway, so let's briefly review. We will finish the last chapter almost. Okay, we still have one thing I have not discussed yet. So basically, last chapter we talking about the thermodynamic functions, where we have totally we introduced the 4 important parameters. I mean, one is the internal energy, right? du equals to what? P ds minus pdv, right? And we also have another one, dH equals what? TdS plus VdP. Correct? Something else? Equals to what? dA equals to what? Nobody else?
SDT minus PDV.
What's that?
Minus SDT minus PDV.
EEG. What?
Minus SDT plus PDV.
Okay. And of course, from them, we can get the Maxwell relationship, okay? So basically, that's the fundamental logic. So basically, the most important use of the Maxwell equation, of the Maxwell relationship, is tells you what about the partial P, partial S, partial P, and function of T, something like that, okay? So you know that we can transform this kind of expression, include the entropy, to something that the measurable parameters. So basically, that's the use of the Maxwell relationship. And let's go back to these 4 parameters. So you can see we choose different kind of the plastic. We choose different kind of the independent variables to describe. Of course, you can change, okay? For this one, we use U as a function of S and V, but we can use S and T and whatever. It's, you can define it. But we already mentioned that how can we change the independent variables. Okay, last time we did some practice, and this practice will continue in homework. And but go back to that one, you can see that since we choose this one, if we include the second law of thermodynamics, we know that this is not equal sign. Instead, this one is smaller or equals to that expression. Okay? So that means if in a system we have if the system has the constant entropy and constant volume, then under the equilibrium, the energy should have the smallest one. It should minimize the energy, right? And regarding this case, if the system has, this is our very intuitive, the aspect, right? If the entropy doesn't change, that means the statistic behavior doesn't change, or like the randomness or chaotic, whatever, it doesn't change, right? It doesn't become messier. Then the answer doesn't change, right? Then by get rid of, and we ignore or if we remove this kind of statistic behavior, and the only driving force that will make the system evolution is the energy, right? And that's what I'm saying? That if the energy doesn't change, then the energy is the only driving force for the environment, for the evolution of the system. We need to minimize the energy. This is our general. Okay. Once again, if the system has a constant entropy and the pressure is constant, then the system should have the lowest entropy, right? Entropy. And if the system has constant temperature and constant volume, then we need to minimize the Helmholtz or Helmholtz free energy. I always put down Helmholtz. Okay. And if the system has a constant temperature and constant pressure, then the Gibbs free energy minimized. Got the points? And it depends on which number you are dealing with. You can choose different kind of descriptions. Okay? That clear? And for most of the case, this one is the most important one. This one is the most important one for most of the case. Because when we do the experiment, synthesis materials and to build alloys by mixing the carbon and ion together, the nickel with silver, whatever. So this reaction or this kind of Lorentz reaction, whatever, phase transformation always takes place, and we always care about the temperature and pressure, right? Because most of reactions happen under the atmosphere, okay, and temperature. Typically, we do not control the volume. We do not control the entropy, right? But we can directly control the temperature and pressure. So this is two parameters we can control during the experiment, right? That's the reason the Gibbs free energy is the most important parameter we care about. Okay? Got my point? And the other beautiful thing is the T and the P are intensive parameters, independent of the volume of the system, right? That means no matter how many alloys or material you are synthesizing or you're examining, we can make sure they are under exactly the same condition by changing the T and P. But for other parameters, they always contain one or two extensive parameters. If you change volume, the energy change. If you change the entropy, the entropy change. Okay? That's the reason this is the one we use the most during the experiment. Okay? And the other thing is, after knowing the Gibbs free energy, basically this expression is for the closed system. The closed system means the system doesn't exchange the matter with other system or the externals. The number of particles conserved. But what if the number of particles changes? Okay? So if you consider that kind of parameter, we can further define this equation or transform this equation in this kind of data form. the mu here is the partial G, partial N, and T and P. That means under the constant volume and the constant pressure and temperature, how the entire Gibbs free energy change as the number of particle varies. Okay, as the number of particle varies. This one we call it chemical potential. Okay, why is it called chemical potential? We can talk about later. Okay, when we talk about the matter exchange or matter. It's not transport. It's the diffusion transport. Okay, matter transport. We're going to explain why we call it chemical potential. Okay. But right now we know that this name of this one is chemical potential. Basically, it's not very accurate, but you can think it that way. That means the Gibbs free energy per particle. Okay, that means how many Gibbs energy are held by a single particle. That is chemical potential. It's not very accurate. But something like this. For example, if we have one system, we have another system, they link to each other, and in between we have a small tube, and then we can exchange the matter between these two. Okay? And then we have one particle move from this side to this side. Then basically it's take the chemical potential of mu from this time to this. Basically it's take that much of free energy from this time to that. Okay? So basically that's why you can interpret roughly, not very accurate. The chemical potential is the Gibbs free energy per particle. Then the question is why we define the chemical potential from the Gibbs free energy. The same thing, because of course you can also define something like this. You can also define something like this. Partial U, partial N. Yes. Of course, you can define something like this. That means how much the internal energy change as the number of particle changes. It's fine, but you should be very careful. This makes the system more complicated. Think about it. If I have a tank, okay, I have a constant temperature and constant pressure. Okay, we have that much. This is, for example, a liquid. Okay, we have something like this. If I remove some liquid out from this tank, from this level to this level, that means that much of the number of particles disappeared or got removed, right? Then the T and P doesn't change in the system, right? That means for the Gibbs free energy, we only need to consider the contribution from this term. However, if we use the internal free energy, we know that if the particle change, the volume also change, right? In order to make the volume unchange, we need to adjust the pressure as well, right? This just makes the description more complicated, right? That's the reason we do not introduce the chemical potential concept from the derivative of U, H, and A. Instead, we use the G, because again, the G is a function of T and P, and both of them are intensive pressures. Okay. But of course, we'll find a very interesting relationship that the partial U, partial N, S and V, this one actually just equals to partial G, partial N, T and P. Okay? You can look for the textbook, they give you the proof. Okay. Basically, it's very simple. It's very simple. The proof is very simple. So let me tell you why the partial U, partial N as a constant S and V equals to partial G, partial N as constant T and P. The reason is like this. Mathematically, right? Mathematically. We know that the G equals to what? The G basically equals to the H minus ST, right? That's the definition of G, or the U plus PV minus ST. Okay? Correct, everybody? And then we can do the derivative on both ends. Then we have dg. We have dg equals to du plus dpv minus dst Okay? And the G is what? G is minus ST plus VDP plus mu dN equals to, and this one is what? This one is the TDS plus minus PDV and plus partial GU partial N, S and V, and then plus D plus VDP plus PDV minus TDS minus SDT. Okay? And the same thing, this one just remove, this one got canceled. Then we just is minus SDT plus VDP plus partial U partial N SV. Okay? So you can see this term equals to this term. Okay? And the same argument, we have this relationship, partial U, partial N, as a constant S and V, we have equals to mu, and the partial H, partial N, at a constant S and P equals to mu, and partial G, partial A, partial N, constant T, and V equals to mu. Okay, you can see that all of them equals to chemical potential, okay? But in different conditions. That's the last topic we missed in the last chapter, okay? And eventually, I mean, when we talk about the phase transformation, we're going to retouch the concept of chemical potential again, okay? Retouch the chemical potential again. So basically, under equilibrium, if the system under equilibrium, eventually we will know not only the temperatures equal to each other, pressure equal to each other, the chemical potential also need to equal to each other. Okay. So this is something we're going to know in the future. But anyway, right now we just introduced the concept of chemical potential. That's the last piece we need to talk about in this semester, in this chapter. And in the next semester, I'm going to teach another class. It's called the phase transformations in materials. And we're going to use the chemical potential all the time. I think for other classes, the same thing. Okay. If you take any class about the metallurgy or whatever, use the chemical potential a lot. If you study something about the semiconductor devices or semiconductor materials, the chemical potential change the name. Okay. In semiconductors, the chemical potential, we do not call it chemical potential anymore. We just call it the Fermi level. Okay. The Fermi level basically is chemical potential of the electrons. Why we call it Fermi level? Because as I mentioned, the electron is a fermion. Okay, that's the reason we call it the Fermi level.
Why do we call fermions fermions?
Why we call it fermion? Because it's after name of Fermi.
What did he do? Like,
Fermi is like he's a physicist, right?
he did like the first controlled nuclear reaction or something like that.
Yes, he's working on like the Manhattan Project. If you want to know about the Fermi, you can go to the Fermi Lab or go to Los Alamos National Lab. They have a lot of things talking about him. If you have a chance, visit the national labs. They're pretty interesting. I've been at the Los Alamos National Lab for about half a year. And I saw their big reactor. You know that because at that moment, I even do not have a worker green card. I'm just the visiting scholar. But I'm going to do something over there. And then 2 safety guards just follow me to this. But it's pretty scary, actually. You know what they told me that do not touch anything behind that glass. What's the reason? Oh, it's going to kill you. It's radioactive. And I asked him, why did you show me around this place? It should be classified. Yeah, yes, it is classified. That's the reason we are here. Yeah. But and he told me that, but if you want, you can use it. Yeah, it's a pretty interesting place. Have you ever been to any national lab before? Some is very boring, some is pretty interesting. Los Alamos is very interesting national lab. It's in New Mexico, on the top of the. It's not called mountain. It's a plateau. It's the flat top. It's called that kind of structure called the mesa or mesa. It means that the mountain looks like this, very sharp cliff and flat top, something like this. So Los Alamos is something here on the top of the mountain. And they have a very interesting national lab. There's another national lab called Sandia National Lab. And you know what's the history of Los Alamos National Lab, do you? You do know that? Yeah. That lab was built just because of the Manhattan Project to build a nuclear weapon. Put all the theories and experiment working in that lab. And basically, it's kind of like it's under DOE, Department of Energy, and it's working on the nuclear energy and nuclear weapon. And because of that, they have quite a lot of they generate a lot of radioactive waste every year. So they have a special pipeline to deliver that kind of nuclear waste from the top of the mountain downhill. They have the pipe. And the pipe is made of the silver. Okay, the whole pipe is made of silver from the top leading to the bottom of the mountain, because that means the heavy metal can block the radiation from the waste delivered inside. And the mechanism of management is pretty interesting. Although that lab is the federal lab, under the name of the Department of Energy, but it's also supervised or monitored by the New Mexico state government. They monitor the environment operation. Basically, the state government have the power to shut down the National Institute. But they are very picky. They come here to do the sampling every day, every week, to see whether they have some radioactive matter leak. And they identify, okay, there's part of the pipe got leak and probably release some radioactive material to the environment. And then the National Lab management said, no, impossible. We checked every, we have an automatic monitoring system. We did not identify any kind of radioactive hazard. So definitely you're wrong, okay? So since we are a national lab, we have more professional facility to do this kind of measurement. Let us measure ourselves. And New Mexico said, yeah, go ahead, just do whatever you want to do. And then they performed the test on their own. The result was that their testing result found even higher radioactive level than the state government. And then they shut down the pipe and do the repairing and also pay a large amount of fund to the state government. That's something that Los Alamos. I mean, Los Alamos had a lot of stories. And there's also very famous and the lab accident happened in the national lab. So if you take the laser safety training, you will hear about that story. But I don't want to talk about it in the class. Okay, anyway, so let's come back to class, and focus on the thermodynamics. Okay, so we're going to talk about the next chapter. Any questions about chemical potentials? Okay. Why I'm talking about national lab? Oh, because you're asking me the Fermi. Anyway, forget about it. We talk about the next chapter. It's called phase. Equilibrium. In one component system. It's equilibrium in one component system. Basically, what is the one component that means? It not means a single element, okay, in one component. For example, water. You have hydrogen, you have hydrogen, you have the oxygen, but it's still a single component. Okay, it's water. It's not salt water, it's not seawater, it's just pure water. Then it's a single component. Okay, if you do not consider chemical reactions, of course, if you put hydrogen and oxygen and burn them, then it's not a single component system anymore. We're talking about water, okay? The first topic, I mean, basically, the structure of the class is, we already finished the introduction of all the fundamental thermodynamics principles. and mathematics. And from now on, we're going to use this knowledge to analyze different kind of thermodynamic systems. Okay? We're going to introduce some fundamental knowledge about phase diagram, but that is not something we're going to focus for this in this class. Okay, we're going to talk about the phase transition or phase transformation in the single component systems, and then we talk about the behavior of gas, liquid, solid, alloy for the rest of the semester. Okay, so I'm trying to be as informative as possible, but I don't want to go very deep into the phase transformations because that's not the task of this class. Okay, for example, like the phase transition about the in the steel, like the marcentite or like the no, we will not talk about it. Okay, the first topic we're going to talk about phase transformation. Okay, so why the phase transformation happens? Okay, again, so we're not going to talk about the dynamics or the kinetics process, like the nucleation, how the phase transition takes place. We only talk about phase transition from a thermodynamic point of view, from argument like minimize the energy, minimize the free energy, from this point of view to explain why the phase transformation happens. But we do not talk about more detailed dynamic processes, like the nucleation, like the diffusion, like the some wave propagation. We don't talk about that. Okay, we don't talk about which state have which form or which phase has the minimum free energy. Okay, let's consider a closed system. Okay. Consider a closed system. Right now we only talk about a closed system, okay? Enclosed system. So what is a closed system again? I just mentioned the concept. Closed system means there's no matter exchange or matter transport, okay? Between several systems. There's only one, for example, a glass of water is fully sealed. Okay? Even if you have vapor, the vapor will not escape. Okay? So that means the total number of particles, number of particles in the component doesn't change, is conserved. Because of that, we do not need to consider the chemical potential. Okay? Only for the open system we need to consider the chemical potential because we have particles move from one part to the other part. But for the closed system, we do not need to worry too much about the chemical potential. And as I mentioned, the most direct control of the system is temperature and pressure. So we want to use the G. We mainly use this equation for the analyze about phase transition. Okay, minus dT plus V. Okay, we're going to start from here to see what's going on. Okay. So first of all, let's consider the situation of constant P. If the pressure doesn't change, we have dG equals to minus sdT. Correct? And with a constant pressure, then the chemical potential is only function of P. Right? It's only function. Then what will happen? Think about it. So right now we just read plot the relationship in this kind of coordinate. So the x-axis SL is T and y-axis is G. So how it change? As the temperature goes up, how it change? So typically for the entropy, it's larger or smaller than 0? It's always larger than 0, okay? It's always larger than 0. Oh, by the way, so there's one chapter in the textbook I totally ignored, okay? It's the third law of thermodynamics. If you feel interested in, just go through that chapter by yourself. Okay, because we do not use that quite often. And the concept, although it's very important, but fundamentally it's important, but typically we don't use that for the practical problems. If you work on theoretical material science, probably want to check that chapter. But otherwise, we just need to know the conclusion. The conclusion is, as a temperature, we can never achieve absolute 0. Okay, we can only approach it, but we can never reach it. Okay. The other thing is, at the absolute 0 temperature, the entropy tends to 0, and the change of the heat capacity roughly equals to 0. The change of the heat capacity, okay, is not the heat capacity, it's the change of the heat capacity. approaching to zero. That's the conclusion. Okay?
Entropy is close to zero, that means entropy is decreasing.
It's decreasing. But actually, it's not always the case. Okay, it's not always the case.
How about we approach from the negative temperature, from negative infinity?
Oh, as I mentioned, negative temperature is not the way. I think I already mentioned the way we achieve the negative temperature is not from this end. Okay, it's not
Yeah,
from
I mean,
here.
can we achieve zero from negative
No.
zero?
No. You cannot. The way we achieve negative is that first of all, we achieve the positive infinity, and then we have a phase transition to reach the negative. It's from the other end, it's not from this end. Okay? You know what I'm saying? But on this end, on this point, there's no definition. Okay? We don't have definition of zero temperature.
What about at the infinity?
Yeah, because I mean, this is a phase transition. We don't have any kind of basically you have some fluctuation, but it's not something we're here. Okay? It's not something here. As I mentioned, the function looks like this. Okay. You know that this kind of like just it's very similar to the arctangent. Okay. You have the positive infinity, and then suddenly become negative. Okay. So we reach negative from this way, not from this way. That means we keep pumping the energy to the system instead of taking the energy away. Anyway, so what's how it looks like? We know the entropy is always larger than zero. Then, as the temperature goes up, the free energy is going down. Right? The free energy should going down in that way. Correct, everybody? This is the first of all, we know that as temperature goes up, the free energy going down. Okay? Basically, that means partial G, partial T, P equals minus S, smaller than zero. Okay? Then let's check what's the second order derivative. Okay? This one is equal to minus partial S, partial T. Correct, everybody? What was that? Partial S, partial T as a constant P. Huh? A louder? What was it say? Just now.
No, that's
That is this one is the heat capacity, right? Remember, we mentioned about this one. Right? So heat capacity is always larger than zero, right? So this one is also smaller than zero. Right? That means the first order derivative of the G is smaller than zero. The second order derivative also smaller than zero. That means the evolution of the G as a function of T should look something like this. Okay? It jumps down faster and faster. Okay? Correct, everybody? Should be something like this. Right? Okay. All right. So then I did not mention what phase it is, right? It can be solid phase, it can be liquid phase. Okay. Then let's compare. Let's assume this one is a liquid phase. Let's assume this one is a liquid phase. Okay? Then with the temperature, let me try it again. Let me make it larger. Let's make it larger. Because I want to make sure the online students also can see it. It's the T. Let's assume this one is the liquid phase. What about solid phase? So, for example, this is the zero temperature. This is the 0K. It's not okay, it's 0K. Okay. So, what is the free energy of solid? Is higher than liquid or lower than liquid?
When you say liquid, is it that point that's liquid, or is it going into?
No, it's all the curve is liquid.
Oh, okay.
Okay. Okay, so for example, like water. And when the temperature goes very low, do you think it's a liquid or solid? It's solid, right? Solid means what? Means the water prefer to stay in the form of ice instead of water, right? And at constant pressure and constant T, do you think which form has the lower free energy? If the water prefer to in form of ice, which one do you think has a free energy? The liquid water or ice? Ice should have lower free energy. That means for the solid, when the temperature approaching the zero, it should be something like this. Correct, everybody? Okay. Then it's something like this. Okay? We know it's something like this. It should also be K, right? And remember, the dG equals to minus S dt. Okay? Minus something like this. We have two. This one is water, that one is S, okay? So this one is liquid. The other is solid. Which one has a higher entropy? Liquid has higher entropy or the solid has higher entropy? Liquid, right? Because liquid is random, right? You have water. Water is something like this. Right? Something random distributed. But for the ice, something like this. You have this structure, the hexagonal structure. Okay? So that's the reason the ice has lower, has more order in it, right? You know what I'm saying? Has high order than the liquid, right? It's so random. So that means the water has high energy than the liquid, or water has high energy than the ice. Correct? That means what? That means for the solid or for the ice, although the entropy also decreases as a function of T, it should decrease slower, right? Correct? Because the slope here, this one is SS. This one is SL, right? The SL should be larger than SS, correct? So that's the reason the curve decreases slower than the liquid. Correct, everybody? That makes sense? And here we have a cross point, right? And then look at it. We know that at the high and low temperature, the H2O prefer to stay in the form of ice, right? And then we increase the temperature, increase temperature, and then here we have this kind of the cross point. And then if we keep moving, make the temperature higher, do you think the water will stay in the? Do you think the H2O will stay in the form of the ice? No, right? Because free energy will be higher in the liquid form, right? It will become liquid, correct? In order to lower the free energy, right? Basically, the phase transition is an effect of the change in entropy, right? So you can see that go from here in the form of the solid and then changing into liquid, right? And this point and this temperature, what's the name of temperature here? Melting point, right? TM, okay, melting point. Simple, right? You can see that we can explain the phase transition with this kind of simple equation. That's it. But of course, it doesn't tell us too much about the information. I have no idea. Okay, let me talk about it. So if we keep the temperature, if we cooling down the water, if we make the water cool down, and then up below this point, the water in principle should turn into ice. Correct, everybody? But do you think that this kind of process doesn't happen spontaneously? Okay, that means although we predict the phase transition from the liquid water to the ice, from the argument of the free energy, but this process does not always happen spontaneously. Okay, I think probably. So again, if you check, give me a second. If you find some YouTuber channels, you can find it's called the super cold water. You can do this experiment by yourself at home. Just put the purified water from the public or whatever. Don't buy the mineral water. Don't buy some spring water. Just buy the purified water. Put it in the refrigerator, waiting for about 8 hours. Take it out, it's still liquid. Okay, and you shake it, immediately turn into ice. Okay. So this all happens. This is called the super cold atom. The reason is, although thermodynamics tells you after below this point, the water should be solidified, but we also need to find a pathway to make sure that this kind of energy is going to be released and make the water change into the into the solid, okay? And this process typically we call it nucleation. That means we need to find some nucleoside for the ice to grow up. If we do not have nucleoside, the water is still water, okay? Again, this is something we're going to talk about in the phase transformation class, not this class. So the reason I'm talking about is, although that's a limitation of thermodynamics. Thermodynamics only tells you the physical process or phase transformation process, whether it's possible to happen or not. Okay? Even it tells you it's possible to happen, it's not necessarily means this process actually happened. But if the thermodynamic tells you, okay, this kind of process won't happen, then it definitely won't happen. Okay? You know what I'm saying? Was there a
So
problem?
is in the phase diagrams, when you say one component, this is what you mean? Like it's just from one phase to another?
Yeah.
And then would there be a region where it's going from, so I learned this in my other thermodynamics class where we have gas and then it goes to a mixture. Like, do we deal with that?
We deal with that. We deal with that. But I mean, I'm going to talk about it. Okay. So what's the ratio between if you have two components? For example, alloy, the copper and zinc alloy. So the ratio between the zinc and the copper are defined not only by temperature and the pressure, is also determined by the chemical potential. But for the single phase, we don't worry too much about chemical potential. Okay? And then the ratio between the gas phase and liquid phase actually are determined by how much heat you put into the system. For example, you have water. If you warm up the water to 100 degrees Celsius, it doesn't boil. It doesn't boil, right? You need to input heat into to keep it boiling. If you just keep the water at 100 degrees Celsius, it doesn't boil, right? Because of what? Because you have latent energy, right? You need to make the phase transition happen, right? That means the ratio is very random, okay? You can make the less vapor than the liquid or more vapor than the liquid. You know what I'm saying? Just by changing how much heat you want to put it. But eventually it will reach the equilibrium. But reaching equilibrium also can be only determined by the temperature and pressure. We're going to talk about the phase diagram. I can explain more about it, okay? But this one is not phase diagram yet. Okay, this one is not phase diagram yet. Basically, phase diagram is a projection of the curve on a two-dimensional plane. Hopefully I have some time to explain that to you. Very fast. I'm trying my best.
Can you please explain a single curve here, like just any?
Which one?
A single curve for the liquid. What does it mean really? This curve.
Is that possible for us to talk about it again after class? Okay. Let me keep going. Yeah, because I want to finish more topic. Okay, so right now you know phase transition, okay? And let's talk more about it. Okay? So you can see that at this, at this phase transition point, we know that the G solid equals to the G liquid. They are equal to each other. That's the point for the phase transition, right? And then we do the derivative on both ends. Then we have the dGsm equal to dGl, right? Then what does it tell us? We know that G is what? G is the H minus Ts, plus or minus. Correct, everybody? Then the dG equals to dH minus dTs, right? Equals to dH minus dTds minus SDT. Correct? And we know we only care somewhere near this point. Okay? Basically, we are talking about a process with a constant temperature, right? We only talk about on this point, so temperature doesn't change. So with that, we can just ignore this term, right? Because the dt equals 0, right? We only talk about the behavior precisely at the Tm, right? So then this term equals 0 because we do not change. We do not talk about the larger area. right? Then we have dg equals to dh minus dS. Correct, everybody? And then we do the integration. Correct? Right? And we know that from the gas phase to liquid phase, what's the delta G here? If we change it from gas phase to liquid phase. We change it from this point to this point. How it change? Basically, delta G is what? Delta G is the GS minus GL, right? What's the delta G here in this case? Delta G equals to GS minus GL, right? So what's the change? It's 0, right?
Yeah.
You are equal to each other. Then we have, from this one we have delta H equals to TL delta S. Okay? That means during the phase transformation, the system, although the free energy doesn't change, the Gibbs free energy doesn't change, the enthalpy change, right? The enthalpy change. Correct, everybody? Right? So what is entropy? And what is entropy in the constant? Well, this is constant pressure process as well, right? This is the constant pressure process, right? Because I mean the pressure doesn't change either, right? So what is the delta H in the constant pressure process? This one is equals to delta Q plus VdP, or well V delta P. So if the pressure doesn't change, this term equals 0, right? Then this one is equally equal to delta Q. Correct? So delta Q is what? Delta Q we call it latent energy, right? Latent energy. Basically, the energy you need to take. That will answer your question. So basically, that's the energy we need to take to change the water into the gas or change ice to the liquid, right? We input energy into the system, but the pressure of the system doesn't change. The temperature of the system doesn't change. So what change? The entropy of the system changes, okay? So we input energy into the system, we increase the entropy of it. Okay, that is the phase transition. So why the entropy change? Think about it. The ice is a crystal, right? It has high order. Then the water is just liquid. It has random molecular distribution inside it, right? The entropy increase, right? If we want to increase the entropy, we need to put energy into it. Okay? Basically, this is the phase transition process. Got my point? But more precisely, this one we call it the first order phase transition. The first order phase transition, okay? This one we call it the first order phase transition. Or phase transformation, okay? Phase transformation. First order phase transformation. So what is the first order phase transformation? Is the first order phase transformation. Okay. First order phase transformation means during the phase transformation, this one is a T, this one is S. Okay, as we increase temperature, the S suddenly change. Okay, for example, this one is ice, this one is water. Okay, we warm it up at the melting point. We put heat into the system in order to melt the water. Okay, and then the entropy of the water changes. Okay, it increases the entropy of the system. If we have a tank of the water at 0 degrees Celsius, and we have ice at 0 degrees Celsius, we mix them together. they just keep the original shape, okay? Water and ice just mixed together. The ice will not melt, the water will not get frozen, right? It's just the ice and water mixture. If you want to melt it, you need to put more heat into it. If we want to make sure that all the water got solidified into ice, we need to take heat out of it, okay? But if we do not put any heat or extract any heat from the mixture of ice and water, it will just keep in the mixture state. You know what I'm saying? So basically, that is the, we call it latent energy, okay? We need to put energy to change the entropy of the system.
That means we are taking away the spontaneousness of the system.
It's not spontaneous. It's just like the equilibrium. It's always under equilibrium.
But if we normally keep ice into water, like put ice into water, it will melt, right?
You have to have the ice, the water temperature of the water must be higher than the 0 degrees Celsius in order to melt the ice. If the water is at 0 degrees Celsius and ice also at 0 degrees Celsius, you mix them together, you just keep the same. You just keep steady, it doesn't change. Okay?
What about you have this super cold water?
Super cold water is a different story. Super cold is the meta-stable state. It's not stable state. If you disturb it, it will spontaneously change into ice and release the heat.
Is it the temperature of the super water is less than 0 degrees Celsius?
It's less than 0 degrees Celsius. Okay, and then remember what's the definition of the heat capacitance? This one equals to T times partial S partial T and P, right? Because we have this discontinuity in entropy, then you will know that the change of entropy, the change of heat capacitance looks like this. It will go up to infinity, literally infinity, and this melting point, and drop down. Okay, so this one is melting point. So that's the feature of the first order phase transition. That means we have the discontinuity on the entropy, and we have the divergent on the heat capacity. Okay, this is a feature of the first order phase transition. And for most of the phase transition we're talking about in the class is the first order phase transition. But is there something else? Is there something else? What about the other phase transition looks like? Of course, we have the second order phase transition. We have the second order, even higher order phase transition. The second order phase transition looks like this. Okay. Oh, by the way, so which terminology? You call it phase transformation or phase transition?
Transition.
Phase transition, right? I have no idea how to phase transformation. So typically, when I'm learning that, I call it phase transition, but in the textbook, it calls phase transformation. Anyway, but I don't think this one will. Bother us too much. It looks like this. Okay, the T and S. It doesn't have the discontinuity. Okay, instead it just has a kink point. Okay, and this one called TC. We don't call it melting temperature. We don't call it boiling temperature anyway. We call it the critical temperature. Okay, it has phase transition. This is second order phase transition. Okay, we don't have discontinuity in the change of the entropy. Okay, it's still continuous, but they have a kink. And for the heat capacitance, it looks like this. Something like this, okay? Or, in our case, probably something like this. Okay? They have something like this. This is second order phase transition. You can also find high order, but I personally do not know high order phase transition. Okay, second order phase transition. For example, like the magnetic order phase transition is the second order. For example, you have the piece of ion, and then you put the magnets on it. You know that they absorb each other, right? But they're going to attract each other, correct? If you have a piece of the ion, if you have another piece of magnet, you put them together, the magnet just attracts the ion, correct, everybody? So if you heat the iron up, then the iron will have the phase transition from we call it the ferromagnets to paramagnets. Okay, then you don't have this kind of strong, attractive interaction anymore, disappear. You can do this kind of experiment. You have a piece of metal, a piece of magnet, you put the needle, whatever, and you use torch to warm it up, you can really jump down. Okay? You lose this kind of the attractive interaction. This is type of the phase transition, because it's from ferromagnetic to paramagnetic phase transition, is a second order phase transition. Okay? Is a second order phase transition. The entropy change, but the crystal structure roughly the same. Okay? Basically atoms configuration is the same. But the electron structure changes. Okay? The electron structure changes. That's the reason we don't have a large amount of the entropy change, but we just have some slightly. I mean the slope of the entropy slightly change. Yeah. That's the second phase transition. Okay? And the second phase transition do not come with the latent energy. Right? So this one is the latent energy. But for the second phase transition, we do not have latent energy anymore.
What kind of energy? I'm sorry, can you spell what you're saying?
It's called latent energy, right?
Oh, okay.
Basically energy underneath, right?
What about like wax, where there's no?
There's no phase transition. It's not phase transition. Okay? Wax, you can consider wax is a super cold liquid. You know what I'm saying? Because for the solidified wax, the order or like crystal or the structure doesn't change much from the fluid phase. Okay? You basically can consider it a super cold liquid. Okay, there's no phase transition. It's similar to the glass. Okay, glass you can consider it a super cold liquid. So you know that there was a crystal. Glass. Glass is not a good example. You can see that the fused, not fused. The fused quartz, okay? The pure silicon dioxide, the quartz crystal. If you melt it and cool it down, it doesn't get a crystal. It doesn't get a quartz crystal anymore. It's like glass. Okay, it's called quartz glass. Okay? It's called quartz glass. It's super cold liquid. Okay, but you can change that to crystal as well. One way is you just keep it there. Okay, and eventually it's going to change from the glass to the quartz crystal. Or you can use some other route to change the quartz, the glass into the crystallized quartz. I have no idea whether this, I mean, the phase transition of the glass or quartz is very important for what's the name of that kind of that area? Basically, it's study the Asian time culture and something like that. Do you know something like that? What's the name of that area? Study the culture and the human whatever in the Asian time.
Archaeology.
Huh?
Archaeology.
Yeah, something like that. That kind of phase transition is very important because sometimes we find some glasswares. Okay? If you put a glassware underneath for a very long time, it will change back to the quartz crystal. And by detecting how many quartz crystal inside the glass, they can roughly judge the time of the glassware. Okay? But it's a very slow process.
So the main point is like if the material is going to phase transformation and it comes back, it have to be in the same state.
Not really.
So ice is converted, is changing into liquid, and then we are taking out the heat. It is converting into ice.
Yeah.
So that's a phase transformation, right?
Yeah.
But let's say you told about wax, right? It's liquid and then it's coming back to its own.
It's not liquid. It's just like instead of calling it liquid
Superheat, solid, or
yeah, instead of name is liquid or solid, it's better for us to say that okay, under a certain temperature, it's lose the capability of flowing. It's not a fluid anymore. Okay, it's not. What's the name of that? I'm not master on that kind of the polymer science or whatever. So it's just a lose the capability of flowing. Okay, basically solidified.
Viscosity.
Yeah, it's not viscosity.
Okay.
It's just like ability to flow everywhere. You warm it up, it can flow, but if you cool it down, it doesn't flow anymore. Okay.
So Professor, does it ever become
Huh?
Does it ever become
solid?
It depends. It's solidified. It's solidified. But in thermodynamics, typically we define solid as crystallized structure. If it's not crystallized, we typically call it a super cold liquid or glassy structure. You know what I'm saying? Glassy structure. And the wax, okay? And also the, you know that there's kind of like called glassy metal. Have you heard about it? Glassy metal. That means you have a certain amount of void and you cool down suddenly. It has no time.
You mean martensitic steel or something?
No, it's not mercantile.
Metallic glass?
Huh?
Bulk metallic glass?
Something like that. So for example, you have some certain metal, you melt them together, cool down immediately. And then it has no time to become crystal. Then it's glassy metal. Okay? It's just like glass. If you drop down, it shatters into pieces. Okay? But what the metal or alloy we're talking about, the mercantile or whatever you mentioned, they have crystal structures. Okay, the body center cubic or face center cubic, it have the crystal structure. But for glassy metal, they don't have this long-term periodical structure anymore.
So usually martensitic steel, it forms needle structures.
The needle structure itself is still crystal.
Okay.
Again, the mercantile is not what we're going to talk about this semester. Okay? I'm going to teach that class next semester, but hopefully no one choose that class. It's really confusing. Mercantile phase transition cannot be fully explained by thermodynamics. Okay. Okay. So let's keep moving. So we talk about the phase transition. Okay, so we already mentioned the phase transition or like the Gibbs free energy changes as a function of T, okay? Then the next topic we're going to talk about the Gibbs free energy. At constant T. That means the temperature doesn't change. And the pressure change, how the Gibbs free energy changes. Then the dG equals what? VdP, right? V is always larger than 0, for sure, right? We don't have negative volume, fortunately. Otherwise, we just drop into it. Because the volume is larger than 0, then as the pressure goes up, the G what? The G goes up, right? It goes up in that way. Okay? Okay. Generally speaking, I'm not saying that always the case. Generally speaking, which one has a larger volume, liquid or solid? Liquid have larger volume, right? Then the liquid should go, the free energy of the liquid should go faster than the solid, right? It's increased faster, right? You can see that eventually, we sometimes, not always, okay? We can find they're going to cross each other, right? They're going to cross each other. And then we have some P, okay? And for example, these two curves are plotted at the melting temperature. If the temperature we're discussing right now is at the melting temperature, then what is the pressure here? What is pressure here? The pressure here is 1 atmosphere, right? Correct, everybody? That's the definition of the melting point. Basically, the melting point is when is the temperature at which the solid to liquid or liquid to solid phase transition happens under 1 atmosphere, right? So that's the reason if we set the temperature at the Tm, then the pressure here, this core point, is just 1 atmosphere. Okay? Any question, problems? Okay. Not much. Simple. let's make the job more complicated. We consider both V and T. Okay, all of them change. Okay, then we have dg equals to minus s dt plus vdp. Both of them change. Both of them change, right? And for the solid state, of course, the dgs, ss, vs. Okay, and for the liquid phase, we're talking about liquid and solid phase, but it's also applied to the liquid and the gas phase, and the gas to the between the gas and liquid phase, between the gas and solid phase. Okay, we just use the solid and liquid phase as an example, but it doesn't change the conclusion between other two phases. Okay, now this one.
Is that squared now?
It's not square. It's just like label. This is solid. This is liquid. Solid. Liquid. Solid. Liquid. It's S. It's not 2. Okay. Then during the phase transition or transformation, okay, during the phase transformation, okay, we know that the dgs equals to dgl. We know that, right? Because the phase transition means that the g equals to each other, right? The g equals to each other. Think about it. When we talk about phase transition in the GT diagram, it's something like this. The cross point is the phase transition point, and for the PG, it's something like this, and this is the phase transition point, right? They always have the Gibbs free energy equal to each other, right? If we consider both factors, the same thing. Then we have, from this one, we'll have minus SS dt plus Vs dp equals to minus SL dt plus VL. Correct? Because they equal to each other. Now this one. Then from this one, we will have dp dt under the equilibrium condition equals to SS minus SL and the VS minus VL. And what's the entropy change? The entropy change is the delta H, the change in enthalpy, right? Divided by T, and Vs minus VL.
What is that? The Q dp by dt?
ER. Sorry. This one means equilibrium state. Equilibrium. Okay, that means you have the equilibrium state between the solid and liquid, or solid and gas, or liquid and gas. Okay. Okay, so let me tell you what the significance of it. So previously when we talk about gas, we talk about liquid. We're always discussing something like this, right? Partial P, partial T, and with a constant V, right? We use the partial. What's the reason why we use the partial derivative? The reason is that P is not only function of T, it's also function of V. We have 2 degrees of freedom. We have 2 parameters. But right now, it's not partial, it's a full derivative, right? That means what? That means under the equilibrium, P is only a function of P, right? Or P is only a function of V. It's only have 1 degree of freedom. Okay, it's only have 1 degree of freedom. What's the reason for that? You can see that, yeah, we only have 1 degree of freedom. For example, what's the reason for that? This is the T, this is the P. Okay, right now I'm going to draw the phase diagram of water. Okay, this one is a vapor phase. This is the liquid phase. This one is the solid phase. Okay? For any system, if you're not under equilibrium, you can be anywhere. Okay, you can be anywhere. Okay? Then if you want to know the phase, you need to know P and T. You need to know two parameters. But if I'm telling you that you are under the equilibrium states between solid and liquid, you have to be on this line. You have to be on this line. Right? Then, if the temperature is decided, pressure is decided. Right? If you move away from this point, you are not under equilibrium anymore. There's no liquid phase, you only have solid phase. If you move to this end, you only have liquid phase, no solid phase. If you have the equilibrium between two phases, we lose 1 degree of freedom. You have to be on these curves, correct? So basically this kind of phenomena, or this kind of the observation is called Gibbs phase rule. Okay, Gibbs phase rule. Let me check whether it's right. Gibbs phase rule. So what does that mean? The Gibbs phase rule is like this. So the degree of freedom means how many parameters you will need to decide the state of the system. Okay, for example, you are in a liquid. We need to know the temperature, we need to know the pressure before we can tell which point it is, right? So the degree of freedom is what? Is 2, right? And if we have two phases, if we have solid and liquid phase, then these two phases stay together, okay? Stay in the equilibrium state. For example, like the water and ice mixture, they stay steady with each other. Then we have to be on this line, right? How many degrees of freedom we have there at that moment? We have only 1, right? So that's the degree of freedom. The degree of freedom equals to the 3 minus the number of phase, okay? This one is the degree of freedom. Hopefully this is not something crazy. Anyway, so degree of freedom, okay? And then phi, where we use phi? Do you know why we use phi? It's very simple, okay? So this is number of phase. It also have the start with something but we do not use p, okay? We also use something that has a similar sound as the freedom. So that's the reason I use phi, okay? Because this is what? This is a great ladder.
At max, we can have 3 degrees of freedom.
At max, you have 3. You have 2 degrees of freedom. You at least have 1 phase,
Okay.
right? We're not talking about there's no phase. Now we're talking about nothing. You at least have 1 phase, right?
So if you're at the center where the solid liquid and
You have 0 degrees of freedom, right? Because this point is unified. It's specifically determined. For the water, this is the triple point, right? Triple point, correct? So what the triple point is? The pressure is the 0.006 atmosphere, and then the temperature is minus the 0.007 some degrees Celsius, something like that. Okay? We don't have any degree of freedom. It's determined. Okay, triple point. The number probably wrong. Okay, check the textbook.
So that means it depends on P and T only, so that's why we...
Yeah, exactly. Okay, so that is called the Gibbs phase rule, okay? But this one is only for the single component, okay? For the single component. So what about if we have multiple components? For example, like the water mixed with salt. Then we have water, we have the sodium dioxide, we have sodium chloride inside. For the general case, the degree of freedom equals 2C plus 2 minus 5, okay? This one, again, degree of freedom, this is number of phase, and the C is the number of component. Okay? For example, you have the salt, you have water, then you have 2 components. Okay, the case becomes more complicated.
You said that's for two components?
This is for multiple component.
Okay.
But for, in general case, okay? But if you only one component, this becomes 3. Okay? That is the Gibbs phase rule.
So alloy transformation and those come under that category?
Of course. All right, so I think we run out of time. I want to draw you a very beautiful picture today, but unfortunately not time. I'm not going to, I just very abruptly introduced the phase diagram of water. It looks like this, right? It's something looks like this, right? But how can we get this figure? Okay, because for the class, we always talk about something like this, right? This is the T, this is the G, and the P, something like this. How can we from this diagram to get this phase diagram? Okay, we have no time to discuss about this topic this time. But anyway, so it looks very complicated. I'll show what it looks like. This is on some line. Let me use some tag. Okay. Otherwise,
I didn't know you knew how to use that.
what's that?
I didn't know you knew how to use that.
You don't know? Right now you know, right? I probably draw it. That is hand draw, okay? So let me briefly introduce. We can spend more time next class to tell you how to draw it. Okay? Basically, we have 3 phases, okay? We have the solid phase, we have the gas phase, we have the liquid phase, right? And then they have different kind of evolution in this kind of PT plane, right? You can see that it's so messy. I will try my best to do the job. But anyway, so you know that because they have different kind of the trend, right? For example, like this kind of the gas phase, and the function of temperature is just faster than other phases, right? Then you have some cross line on this one. The 2 point has a cross line, right? And you have gas, you have liquid, and you have several cross lines. And if you project this cross line on the 2-dimensional reference frame, you have this kind of phase diagram. Okay? I will try to draw better next time. I try my best to find some beautiful 3D print of the Gibbs free energy as a function of P and T. Unfortunately, I cannot find anything. So I have to draw it by hand. Anyway, so I think that's pretty much for today. We're going to continue our topic next time.
What is C? What component?
Number. Number. Yeah. Sharp. Yeah.
Still have one more question.
I'm going to talk about this.
So was this like energy versus temperature?
Next day I can also. I'll try to.
Come to the office if you want.
Oh, I'm going to another conference.
Oh,
Like,
you already can jump in that.
I have you.
And is this temperature energy? What is this?
Energy.
See, what is this?
Yes. Not your parents, not you cannot ask your parents.
Oh, my parents.
Yes, you already told me.
Yeah,
See,
yes, you cannot ask your parents.
she's so happy. She's okay, you can use any hand.
Yeah. Even parents you can't ask your
Right.
parents.
The bottom that trigger. So, the thing is like this. Okay, this, but can it be more precise? This one. Let's try it.
You don't have to
So,
like that.
as the
Yeah, I can't buy a book now.
Yeah.
But I think
we define
we define the topic, right?
Yes.
Okay, that is allowed.
See?
So the negative temperature typically can be implemented in the two level system. We only talk two energy levels. If you have multiple levels, it's really hard. You can just do it. But we typically talk about, we only, not only that one, atoms, molecules can also revive. But be very careful, the negative temperature is a very localized concept. Okay, only defined between these two energies. So you can see that as the energy goes up, the entropy goes up, right? The entropy. Because I mean we are pumping the molecules from the lower level to the higher level. That's the reason the energy goes up and entropy goes up. But if we have more than half of the particles already occupied a higher level, we still keep putting energy in, then the entropy will saturate and eventually drop down, right? Because eventually we'll get something like this, right? This state we call is population reverse, right? Population reverse state. Then the entropy going down,
It's just 1 point.
right? But by this definition,
Yeah.
it's a U